So our next aromatic reaction is known as the Friedel-Crafts Alkylation. And this reaction dates back to the 1800s. And when we look at what this reaction does, at least initially it's going to be one of those reactions that looks nothing like what we just covered, the halogenation. But the reason I cover them in this order is because it turns out this reaction is very similar to the alkylation, at least based on its mechanism. So in the Friedel-Crafts alkylation, we're going to take an alkyl halide, and we'll just start with chloromethane for this first example, and a Lewis acid like aluminum chloride, and we get substitution of that alkyl group onto the aromatic ring. So this is a reaction that's going to allow us to make new carbon-carbon bonds. So how does this work mechanistically, and why do I say it's so similar to halogenation? Well, if you recall with halogenation, the first step was that the Br2 attacked the Lewis acid FeBr3, to give us this intermediate with the partial negative on the metal and the partial positive on the bromine. Well, in the Friedel-Crafts alkylation, the reaction in the first step is the same. The electrons in the carbon-halogen bond will attack, in this case, an empty p orbital on aluminum, and form an intermediate that is very, very similar to what we had in the halogenation. Yes, the nucleophilic species, the electrophile is different. Yes, we have a different metal. But other than that, it's largely the same type of intermediate. Just like with the halogenation, if you recall with the halogenation, we said that the halogenation behaved even though it's not actually a cation, it behaved as if it was Br minus. Br plus. Same thing here. Even though this isn't an actual carbocation, it's going to behave as if it is a carbocation. So this is going to behave as if it is a methyl cation. Now, we wouldn't have a methyl cation. We know that those are too unstable. But it's the equivalence of a methyl cation. And so now that we've done that, our aromatic ring can attack and cause the carbon-chlorine bond to fully break. And so that leaves us with our sigma complex plus AlCl4 minus, which if you recall from halogenation, we had FeBr4 minus. So again, a very, very similar intermediate. From here, that extra chlorine that's now negatively charged on our aluminum reagent will come in, remove this proton, and reform the aromatic ring. So an almost identical mechanism to what we learned for halogenation. Although at this point, this is where we run into a major difference. And we have two major concerns with this reaction. again, we can see that the aluminum chloride is catalytic. It gets reformed. Now, with halogenation, that wasn't a problem because halogens, as we're going to learn later on, make aromatic rings less reactive because they're electron withdrawing groups. But alkyl groups, we know that alkyl groups are electron donating. So addition of an alkyl group makes the ring more nucleophilic. And so with Friedel-Crafts alkylations, you often have the concern of more than one R group getting added. So that's our first problem. The second problem, you know, we're dealing with a carbocation-like intermediate. And that, as we know, has the potential to lead to other issues, as we've seen with many other mechanisms that involve carbocations. And it turns out that's such a significant problem that even if we make the carbon chain one carbon longer, we run into issues. So let's say that instead we use propyl chloride. Mechanism starts out the same. Carbon-chlorine bond attacks the aluminum. But this carbocation, like intermediate, if it has the ability to go to something that's more stable, it will. Because we know that secondary is going to be more stable than primary. And so if you try and do this Friedel-Crafts alkylation with even a 3-carbon alkyl halide, you're going to get a rearrangement that takes place to give you a more stable intermediate. And so instead of propylbenzene as the product, you end up with isopropylbenzene. So how do we get around these problems? Because both of these, while the Friedel-Crafts alkylation can in certain situations be a very useful reaction, there are plenty of other situations where the two issues we just showed, reacting more than once, as well as these rearrangements, can be very limiting in what we can actually do to this reaction. So a similar reaction, but one that can help us to solve both of these, found by the same two chemists, Friedel and Crafts, is the Friedel-Crafts acylation reaction. And the major difference is that instead of an alkyl chloride, we use an acid chloride. So how does that help us? And does it solve both problems? So the mechanism starts out the exact same way. The carbon-chlorine bond attacks the aluminum. But immediately we get a slight difference here. And that difference is that the oxygen can add in its lone pair and kick out the chlorine completely. And this has a resonance form that looks like this. These species are known as an Acelium Ion. Well, the Acelium Ion has the carbocation, but that positive charge can also be up on the oxygen. So in other words, that cation is now shared between the carbon and the oxygen. And so due to this resonance and the fact that that positive charge is shared between the two atoms, there's no rearrangement that takes place. So no matter how long our carbon chain is, we can get away with it in this reaction. It's not going to rearrange. So we've solved one problem. And we'll talk about the other problem after we work our way through the rest of the mechanism. So nothing all that interesting going on in these next two steps. Aromatic ring attacks the electrophile, and we form our sigma complex. And then just as it did in the alkylation, the AlCl4 minus grabs the proton, electrons shift down, and we regain aromaticity. Now, in the alkylation reaction, we were done at this point, but not in the acylation, because it turns out that oxygen likes to bind to aluminum, and so the AlCl3 that was regenerated in this step will actually become attached to the carbonyl. And then upon quenching the reaction, we get our carbonyl back and that oxygen-aluminum bond breaks. But two major factors here. So because of this last step, first of all, in this reaction, the aluminum chloride is no longer catalytic. Initially, it looks like it is, but it turns out it isn't because it becomes attached to the oxygen. And so it's needed in a stoichiometric ratio. But in addition, carbonyl groups on an aromatic ring is deactivating. So by putting that carbonyl on there, we're getting a product that is less reactive than our starting material was. And so it's not going to be able to react a second time. Now, so we've shown one way that this solves our problem. We're not going to get over alkylation, and we're not going to get rearrangement. But now we're left with the carbonyl. What if we only wanted the carbon chain? Well, two things to think about. One is that having this carbonyl lets us do, all sorts of other things in terms of synthesis. Now we've got a carbonyl here, and we've got all those chapters of carbonyl chemistry that we've just finished available for synthesis. But if we don't want the carbonyl and we wanted just that alkyl chain, and it's a long alkyl chain, one we couldn't make with an alkylation reaction, what can we do at this point? Well, there's a couple things we could do. One is a reaction we have already learned, which is to use hydrazine and base at high temperature. Hopefully you recall this is the Wolff-Kishner reaction. And that allows us to remove the carbonyl, replace it with a pair of hydrogens. Or we can use zinc and hydrochloric acid in a reaction known as the Clemmensen reaction, which will do the same thing. So the Friedel-Crafts reactions give us a lot of options in terms of being able to put new carbon-carbon bonds onto our aromatic ring. and then still give us directions that we can go with them after. There are, however, two major limitations for the Friedel-Crafts, and this is for the alkylation or the acylation. The first, you can't have any amines present in your aromatic ring. And that's because if you do have any amines, they will react preferentially with the aluminum chloride. And obviously, if you've used up the aluminum chloride, then no reaction can take place. The second one is in a Friedel-Crafts reaction, you cannot have any electron withdrawing groups. Any electron withdrawing groups will deactivate the aromatic ring to such an extent that it's no longer a good enough nucleophile.